Hi everyone and welcome to EE323 Lecture 6. Today I'm going to be talking about a very important circuit called diode rectifiers. These are rectifiers that convert AC to DC based on diodes. You can find this in your book in section 4.6. Okay, let's get started here. So just to put this in context and to understand where diode rectifiers are used, I'll show you a little diagram here from your book that explains where an example shows an example of a wall outlet, and then the ultimate, the other end of the circuit is going to be some load, which might be, say, your computer or a cell phone charger or something like that. And we'll see the process how the wall AC voltage gets converted. And so we start with some 120 volt AC on the left side. This is a pretty high voltage, and there's reasons for doing that. But then we go through this transformer which steps down the voltage, and still AC. The voltages are always AC after the transformer. But now the voltage is lower, AC voltage, which we label as VS. So after it goes through the transformer, it's still AC, but the voltage is lower. And then it goes through the diode rectifier. And what the diode rectifier does, it converts the negative half cycles to positive half cycles, as we'll see in this lecture. But still, if you look at this voltage here, this waveform, it's still not super useful. And then we go through a filter, which we're going to learn about. And this essentially kind of smooths out the pulses to make it a little bit more useful for electronics. And then the final circuit here is something called a voltage regulator, which we'll learn about next time. And this basically makes a very constant DC voltage at a specific voltage that's suitable for the load. And so in this case, this voltage depends on what your load requires. Some loads require 5 volts, other loads require different voltages. So today, the focus is going to be on this diode rectifier. Okay, so let's move on and talk a little bit about why we use AC to begin with. So the US and actually almost the whole world uses the AC current electrical grid, and you might ask why. Well, it wasn't always the case that it was obvious that we should or did use AC. And in fact, in the 1880s, there was a big debate between Edison, who espoused DC, and Tesla, who said that we should use AC. And as you can see, AC eventually won favor. And one of the reasons that it did is that it was easy to convert AC to different voltage levels using step-up and step-down transformers. At the time, there was no equivalent circuit or technique for DC. We didn't have solid-state semiconductor voltage regulators back then. If we did, well, maybe it would be a different story today. But that was a big motivation for using AC. And the reason that it was important to use transformers is that it's really desirable to distribute power at high voltage but low current. And the reason for this, if we think about the losses in a distribution network, the losses go as I squared R. And so what you'd really like is low current, right? And obviously low resistance. But the lower the current, the lower the loss. So for the same power, you'd like to distribute the power at high voltage and low current, and then you get to a transformer, and then you step it down to a more reasonable voltage so people don't get in danger in their homes. And so this was really only practical using AC at that time, and in fact, transformers are still widely used today in our homes and for power distribution. That's not saying that DC doesn't have some advantages. In fact, DC does have some advantages. It has some loss advantages, specifically when we're talking about long cables and having to do with straight capacitance. Because as you know, capacitance only is a function of AC, right? You have to charge and discharge a capacitor. At DC, capacitors look basically like open circuits and there's no loss there. So there are some advantages to DC as well. Okay, so let's get back to our rectifier. And we'll start with the simplest rectifier, which is called the half-wave rectifier. And um, what we'll see, okay, is that let's suppose we have the circuit here. We have some source. This is going to be an AC source coming in. And we're just going to put it through a single diode D, and then we're going to have some load resistor R, and we're going to look at the output voltage V. So a very simple circuit, AC voltage, single diode D, output R. And so this waveform on the left, this AC is representing Vs. And what do you think the waveform would look like on the right? That's assuming that the diode is ideal in this case. Well, for this to pass current, for the diode to pass current, it has to be forward biased. And so therefore, the diode is only going to pass current, and we're only going to get a voltage at the output, right, when the input voltage is positive. So when the input voltage is positive, like for this window here, we're going to copy it, and we're going to get a voltage waveform that looks like this. But when the input waveform is negative, the diode is reverse biased, right? And V out is equal to 0 if Vs is less than 0 volts. So we get nothing here. And then we wait for it to turn positive again, and we get a waveform that looks like this, and so on. So we can see how it's rectifying, right? It's converting AC to a rectified version of the AC. But you can see right away this has some advantages, some disadvantages. First of all, why do we need rectification? If you look at the average of the voltage of the sinusoid, the average is obviously 0. But now if we look at the average or sort of DC value of the voltage on the right, it might be some higher, it might be some significant DC value. But notice that we're getting rid of all the energy associated with the negative waveform, the negative part of the waveform, and that's definitely going to be a problem. So let's look at this with a little bit more accurate model, slightly more accurate. Let's call it the constant voltage drop model. And so it's the same circuit. We have our diode D, but we're going to have a constant voltage drop, and we'll call that constant voltage drop, in this case, VD for the voltage drop across the diode. Remember, the constant voltage drop diode model looks like this, right? It's like the ideal diode, but shifted over a little bit. And this voltage here is VD. And so if Vs is less than VD, right, we're reverse bias in that case, and the output is 0 volts. But if Vs, the source voltage, gets to be greater than Vd, then we have an output voltage, which is the source voltage minus the diode voltage drop. So we can see what happens is, if we look at our AC waveform, that the black is the waveform coming in, right? And then the blue is the waveform coming out. It doesn't turn on. We don't get the diode on until a little bit of a delay. That is until Vs gets to be this Vd value, and then we can see the blue going up. And as a result, the peak value is Vs minus Vd, so it doesn't reach the peak value. So this is a half-wave rectifier with a more constant, with a constant voltage drop diode model. For your record, this is figure 4.21 in your book. Okay, again, we're losing a lot of energy here because we're throwing away all these half cycles, right? And so that brings up the idea, well, how do we make a rectifier that doesn't lose the energy from those half cycles? And that is what we call a full wave rectifier. For your reference, this is figure 4.22 in your book. And so the full wave rectifier is a technique to use both positive and negative waveforms to generate your output DC-like voltage. And so there's a special transformer that's used in this case. This is called a center tap transformer. And what this does is it takes this AC line voltage coming in, and it generates two waveforms coming out, both magnitude Vs, but with reverse polarity. So you notice that the polarity on diode D1 and the polarity on diode D2 are opposite, but the same waveform, but opposite, right? Opposite phase. So let's look at a specific case. Let's look at the case where the AC voltage coming in is greater than 0. That is, we're in the positive part of the cycle for the AC line voltage, right? And in that case, Vs is going to be positive, and in that case, diode 1 will be turned on, right? So diode 1 is forward biased, right? And we can see that V out is going to be greater than 0 volts from the current through D1. Now, what about diode 2? Well, in that case, we have a negative voltage on diode 2, right, because the opposite phase of the source. And in that case, diode 2 is reverse bias. And nothing is essentially happening with diode 2. Okay, let's look at another case here. Now we're going to look at the case where the input AC waveform is less than 0. So now the negative portion here of Vs from our center tap transform is actually going to be positive, and the positive side of Vs is going to be negative. So in that case, D1 is reverse biased, and D2 is forward biased, right? And V out now is going to be greater than 0 from current through D2. So now we're going to get current flowing like this up into our load. Whereas previously, in the previous situation, we had current flowing like this through our load. So notice that we get current and a positive voltage at the output regardless of the input phase. And so what this results in is we get rectification for both the positive half cycle and the negative half cycle, right? And in the positive half cycle, we're getting rectification from D1, and in the negative half cycle here, we're getting rectification from diode D2. Again, this is figure 4.22 for your reference. So you can see now why it's called a full wave rectifier, because both sides of the waveform are getting rectified. And if you looked at the sort of DC or average voltage now, it would be way up compared to the, maybe not that high, but it would be much higher than the half wave rectifier. So we're getting, it's more efficient in that sense. Okay, so one of the downsides of this full wave rectifier is that we need this sort of special and fancy transformer, this center tap transformer. There is in fact another way to do this, and this is called the bridge rectifier. And this is a very commonly used circuit, and we'll talk about it here for your reference. This is figure 4.23 in your text. So the bridge rectifier uses 4 diodes. You can see them labeled D1, D2, D3, and D4 in the circuit below. This does not require a special transformer, just a conventional transformer, and it also achieves full wave rectification. So essentially what happens is when this Vs signal is positive, we'll go through this in a second, but we're going to see that diode D1 and D2 turn on, and we get a current path like that. And when the phase of the input Vs switches, we're going to get a different pathway. It's going to go through D3 and through like that. And so when the Vs is positive, D1 and D2 are on, and D3 and D4 are off. And when Vs is negative, D3 and D4 turn on, and D2 and D1 are off. And you can see that from this GIF here. It's the slightly different connection, but you get the idea. If you want to see this, this is from Wikipedia. Just look up full bridge rectifier. And you can see that as the input phase over here changes, then which diodes are on switch. All right, so we get one pair on, and then the other pair on. One pair on, and then the other pair on, and so on. So let's go through that a little bit more closely, how that works. Okay, So let's talk about the case where our input AC voltage is greater than 0. In other words, we're looking at this positive half cycle. So we have positive voltage, right, at positive voltage at positive. So in that case, what we're going to see is that diode 1 is forward biased. And if you look at this connection here, then diode 2 is clearly reverse biased. I'm sorry, diode 4 is clearly reverse biased and open. And so then we're going to get current flowing through our load like this, right? And this is going to be, the negative terminal is going to be negative. So you can see that VD, that diode D2 is going to be forward biased and diode D3 is going to be reverse biased. So just to recap, D1 and D2 are forward biased, D3 and D4 are reverse biased. And so what we get is this rectification here, where this is from D1 and D2, right? By the way, this is figure 4.23 in your book. And one thing to notice here is the diode drop. So as you're going through this pathway here, you get one diode drop, and then through our load, back over here, and a second diode drop. So the peak voltage now is down by 2 VD, right? Not 1 VD in the cases we saw earlier. So we get 2 diode voltage drops around each loop. And now we'll see a very similar situation when VAC is less than 0. In other words, this sort of becomes the positive terminal. And in that case, we see that diode D3 gets forward biased, right? And then it flows through the resistor, and diode D4 gets forward biased. And you can also see that the positive terminal becomes negative, and D1 becomes reverse biased, and D2 is reverse biased. So in that case, we can see that this portion of the waveform here is from D3 and D4. Right? This is the case where VAC is less than 0. But again, notice we have 2 diode voltage drops, right? And also notice that the pathway that the current takes through the resistor is the same, hence the same polarity on the output voltage shown in blue here, right? It's always positive. Okay, so what are some key rectifier specifications that we should be aware of? There are some. One is that current handling capabilities of your diodes. In other words, how much current can you pass through? What's the highest current that they can handle? And that's going to impact what kind of load you can connect to this. The other, another important specification is called the peak inverse voltage. And what you'll see in these diodes is that while some of the diodes turn on, the others are reverse biased. And so this peak inverse voltage is the largest reverse voltage that can appear across the diode without breaking it down. And if you go back and you look through the previous rectifiers we looked at, the half wave has a peak inverse voltage of Vs. The full wave with the center tap, right, because we're creating 2 voltage waveforms that have magnitude Vs, what we find is that the peak reverse is 2 Vs minus Vd. And in the full wave, or the bridge rectifier, we find that it's Vs minus Vd. So again, this is another advantage of the bridge rectifier over the full wave, is that it has a smaller inverse peak inverse voltage, which is better for the diodes so they don't break down. Okay, so what are some of the limitations of rectifiers? Well, the most important limitation of both full and half wave is that the output waveform, this is a full wave output waveform shown here with this voltage variation, which is approximately equal to Vs, but minus 2 Vd in this case. But still, you wouldn't want to hook up your cell phone to, or your laptop to, a waveform that looks like this, right? It would turn on and then turn off and then turn on and then turn off. So this is not quite DC or constant enough to be useful. So the question that comes up is, obviously, how do we reduce this variation? So one way we can do that is pretty straightforward. we could just add a capacitor at the output. So what happens if we just take our half-wave rectifier and we add a capacitor? Well, what's going to happen during the positive half cycle, the diode is going to turn on, right? And we're going to charge the capacitor through the diode. But then when it goes to the negative half cycle, right, this is now the output voltage is charged. There's nowhere for the current to go because you can't have current flowing in a reverse bias diode. So what's going to happen is that it's going to charge up and then maintain a constant voltage over time. Now, this is looking much better for powering your electronics, right? You have a constant DC voltage rather than this, kind of waveform that looks like that. So it looks like we're done, right? Constant DC voltage at the output, we're all finished. Not exactly. And the reason is that we haven't applied a load yet. And a load is going to draw current off the capacitor. And so this is now a more realistic situation. We have essentially a half-wave rectifier with the diode. We've added this smoothing capacitor C, and this resistor here is representing the load. This is the circuit that we might hook up to our rectifier, the cell phone charger, for example. So what we're going to see is that if we look at this waveform down below, that we're going to charge up to some value. Let's suppose we start at this point here, but now we're going to discharge the capacitance through the resistance, and it's going to discharge, 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 and then charge up again and discharge, discharge, discharge. So it gets much flatter, but still not super flat. And this voltage here, when the capacitor is discharging through the resistor, is VR, or what we call the ripple voltage. And this is called, or you can refer to it as voltage ripple. You'll see it written many different ways. So that's VR, or the ripple voltage. And what we can see here is that during this time, right, the capacitor is charging through the diode. So the cap is charging. And then during this time here, the cap is discharging through R. Now, obviously, we'd like the capacitor, it seems clear, to be really large, right? Why? So it can store a lot of charge. The larger the capacitor, we'll see that the smaller the ripple. And we can actually quantify this by looking at the currents. We can say that the current through our load, IL, is V out over R. The current through the diode, just by KCL at this node here, is going to be the current through the capacitor plus the current through the load. And therefore, we can write that the current through the diode is this combination of the two, right? Where the current through the capacitor, C dV dt. And so what we'd like to do is choose a large C so that the time constant associated with the RC discharge, right, is significantly larger than the period T of our AC signal. And so we can further quantify this, and we can actually calculate what this conduction interval is. We can calculate the conduction interval, and we can calculate what the voltage ripple VR is based on some pretty simple assumptions. So let's look at the end of the discharge, right, at this point here. All right, we can say that the change in voltage, which would be V peak minus VR, is, so that's this voltage right here. So we're going to have a decaying exponential with an RC time constant, right? And we can say it's approximately equal to V peak times e to the minus t over RC. That's just an RC time constant, and it's only approximate because we're saying that the time is t, and in fact the period is not quite t because we have this charging period of delta t. So that's an approximation. Now, let's assume that RC or CR is much greater than t. In that case, we can approximate this exponential. Again, remember, e to the x is approximately equal to 1 plus x for small x. And so we can say that if we substitute this in for this approximation and we simplify, we end up with the VR is approximately equal to Vp times T over Rc. If we substitute in 1 over F for the period T, and we recognize that Vp over R is the current through the load, we end up with the voltage ripple as a function of IL, the current through the load, and Fc. And so we can clearly see that for higher frequency, we're going to get lower ripple. That makes sense, right? Because it doesn't have time to discharge. For larger capacitance, we're going to get lower ripple. Again, that should make sense. The larger capacitor, the more charge it can supply to the load. And for a smaller load, we're going to get a smaller load current, IL, we're going to get less ripple. By the way, this is equation 4.26 in your book for your reference right here. And so we can also go about calculating the conduction interval, delta T. And this is equation 4.28 in your book. And this, again, just calculates the time it takes to charge a sinusoid, or to raise a sinusoid, again, using approximations. And the approximation in this case is the cosine x is approximately equal to 1 minus x squared over 2. And if you do a few substitutions, it's fairly straightforward to calculate this time. And you can see that the conduction interval is going to depend, again, on the frequency, high frequency, smaller conduction interval, right? And the ratio of VR to VP. Okay, so we can notice that in this example here of what we call a peak rectifier, that we're looking at the waveform from a half-wave rectifier. That is, we did not rectify this negative portion of the cycle, right? And so we can also apply this peak rectification technique to a full wave rectifier, which we would call a full wave peak rectifier. And you can see now that each, the positive and negative portions of the AC signal are rectified. And you can see that the ripple is the same. We define it in the same way. So this would also work for the full wave rectifier. But you can, hopefully it's intuitive that the ripple for the same size capacitor and same size load, the ripple is going to be reduced by about a half. And that is simply shorter time for the capacitor to discharge to the resistor, so we'd expect the voltage ripple to be smaller. Alternatively, we could say that we could use a capacitor with half the value for equal ripple to the half-wave rectifier. And that capacitor value turns out to be important because using a capacitor that's half the size is going to end up with a cheaper and smaller solution. Okay, and that is it for this lecture. Thank you very much.